So to summarize the observations of the photoelectric effect, the intensity of the incident light, and incident just means the light that's being shown upon it, does not affect the energy, only the number of emitted electrons. The energy of the electrons depends on the frequency, and there's a certain minimum frequency that has to be met. And the third thing, which is kind of assumed maybe but not directly stated until here, is that the electrons are emitted immediately. As soon as the light is shown on it, if it's above the critical frequency, electrons are emitted. There's no time delay. There's no, well, let's sit around and wait for the electrons to absorb the light, anything like that. It's an instantaneous effect. If light that is at the critical frequency or greater is shown upon the photosurface, electrons are going to be emitted. Now here's where the problem with classical physics comes in. According to classical physics, if we continue to shine that light upon the photosurface, the electrons should be absorbing more and more and more energy as time goes on, and eventually they should gain enough energy to be emitted from the photosurface. The idea here is similar to if you were standing on stage and all of the stage lights were on, and as that light is shining on you, you're getting hotter and hotter and hotter. Your body is absorbing that energy, and so gradually you're getting hotter and hotter. You start to sweat. The electrons, according to classical physics, should be able to gradually absorb that energy regardless of the frequency, and once they get enough energy, they should be able to get off of the photosurface and be ejected. That didn't happen. The solution to this was proposed by Einstein, and this is where the quantum theory comes in. This is where the particle theory of light is first presented. Einstein's solution was that light doesn't necessarily always behave as a wave. It can also act as a particle, as a photon, as a packet of energy. And he called these packets of energy quanta. And he came up with an equation to determine the amount of energy in a quanta of light, which is shown down here. E is the energy in the photon equals h, which is Planck's constant, times the frequency of the light emitted. So, in this equation, energy is in joules. H, which is Planck's constant, and that's given down here, 6.63 times 10 to the negative 34 joule seconds, times the frequency of the light in meters. And so, again, just from this equation, you can see the direct relationship between frequency and energy. Since Planck's constant is a constant, that's not going to change. So if the frequency goes up over here, the energy in that photon over here is also going to go up. And so with this idea of photons of light, the photoelectric effect was able to be explained. When the photon hits the photosurface, an electron on the photosurface will absorb that energy. Now, depending on the frequency of light, there's going to be different amounts of energy in that photon. Part of that energy in the photon is going to go into getting the electron off of the photosurface, getting it off of the surface of that metal and ejecting it. Anything that's left over is going to become kinetic energy of the photoelectron. And so if the energy associated with that particular frequency of light was less than the critical frequency, the electron wouldn't absorb enough energy and so wouldn't get kicked off of the surface. If the frequency of light had energy that was equivalent to the energy it took to get off of the photosurface, the photon would be ejected but wouldn't have any kinetic energy, so it would be ejected but wouldn't move. And if it had more than that energy, it would be ejected off of the surface with some kinetic energy. It would be moving once it got off. Now, that energy that it takes to get the electron off of the photosurface is what we call the work function of the surface. And again, that work function is directly related to the material that makes up the surface. So different metals are going to have different work functions. And then this little Greek symbol here is what we're going to use for the work function. So we can now look at the kinetic energy of the emitted photoelectron with a slightly different equation. Again, here E subscript K is the kinetic energy of the electron after it's been kicked off of the photosurface, is equal to HF. And again, remember, HF, this is the energy in the light. It's the energy from the electromagnetic radiation minus, and this Greek symbol here, this is our work function. And so this HF is the total energy that's absorbed by the electron. The work function is the amount of energy that it takes to get off of the surface of the photosurface. And so everything that's left over becomes kinetic energy of that electron as it moves away from the photosurface. So again, to just quickly summarize the three possible things that can occur when we shine light on a photosurface. If the energy associated with the photon is less than the work function, then nothing happens. There are no electrons emitted. If the energy of the photon is equal to the work function of that surface, then the electron is going to be emitted from the atom, but it's not going to have any kinetic energy. So it'll be ejected, but it won't be moving. If the energy associated with that frequency of light that's shown on it is greater than the work function, the electron is going to leave the atom and it's going to have some kinetic energy associated with it from that equation that we just looked at.